Is the most popular dry etching system used in the industry. Okay, in these systems, iron plays an important role in the etching process. At the planar type and the barrel type, we neutralize the ions and fragmentized fluorine atom itself plays an important role in chemical reaction, right? But in this RIE system, the ions plays an important role, and the characteristic of this chamber is we use the RF, and we can have a DC potential. We call that self-bias, okay? If you apply the RF, this is the AC, but the ions and the electrons, the mobility of ions and electrons is very much different. See, the electron is very much, has a very high mobility compared to the ions, so that even if you apply the AC between two electrodes, it forms a self-DC bias, okay, because of the difference in the mobility between ions and electrons. So because of this DC bias, we form a self-bias. We call this the self-bias, and with this self-bias, the ions, for example, the fluorine ions or argon ions, whatever, this is going to be accelerated with this DC bias, okay? And the pressure should be relatively low compared to the planar and the barrel type reactor, okay? Because the accelerated ions has to have a large mean free path. Mean free path means the distance between the collisions, right? So etching is anisotropic, and the temperature kept relatively low temperature to have an anisotropic etching. Okay, if the chemical reaction becomes important, then the directionality is going to be isotropic etching. So we do not want to have high temperature. Okay, and in general, selectivity is worse than with the chemical processes. The selectivity has to be bad, because it's more or less the physical collision becomes more important than the chemical reactions. Okay, if the chemical process is important, then we can secure the selectivity. But the physical process is important, then we are going to lose the selectivity. Sacrifice some part of the selectivity. But we can increase the anisotropic nature of the dry etching. And the most conditions, ions and the neutrals both play an important role in etching. Okay. So chlorine is going to be ionized with argon, like this, and the fluorine is we are going to have F plus ions in here, not only the neutral but also the ions, so that it can be accelerated by the DC bias to have an anisotropic etching. So in order to have anisotropic etching, we have to prevent the chemical reactions. Has to be prevented. Okay? And we want to have a ion for etching. Okay, DC bias. So with these two things, we can have anisotropic etching, and an RIE, as you can see, it's named reactive ion etching, RIE, reactive ion etching. We have some chemical reactions, and we have ionic nature to have acceleration and directionalities. Directionality, okay? And reactive means we are going to have a chemical reactions. So it's a kind of a combination between the physical process and chemical process. Okay. Advantage of this RIE, excellent dimensional control because the nature of anisotropic etching, right? And the easy process, simple gases. We just use the fluorine gas and argon gas to get ions. Disadvantage, radiation damage. It relatively have high energies for the directionality. Severe photoresist erosion because the etching rate is very high, so that the photoresist may be etched fast. Okay, contamination with sputter off materials, okay, and selectivity has to be poor because we involves the physical process. So it is nice to have a dimensional control, and we are going to have very sharp edges, just a reflection of the mask patterns, right? But this stiff gives you the residues, something like this after the etching. Here, if you do the RI etching, because of this anisotropic nature, you are going to have silicon oxide and silicon, for example. You can have a very steep walls after the etching by RIE, okay? And then if you deposit some metals on top of this for the later process, then the metal is going to be deposited something like this. So when you look at here along the wall, side wall, the height to be etched is going to be about 3 times thicker than the other part, so that if you do the etching, here the anisotropic etching again, not with the wet etching, then because of the directionality, you're going to have some materials left along the side wall of the SiO2, and we call this residue. Okay, and then if you think it's a two-dimensional way, then this is going to be formed something like this, okay? So this whole thing is just a metal, and this may connect to the next transistors we call short. Okay, this will lead to the short problem. So this residue is a kind of a problem that we can have in anisotropic etching. So in order to relieve that problem, what we can do is we can do the tapering. Typically, after the RI etching, you are going to have something like this, and then you do the blank etching. Blank etching means without any mask. You're going to etch just a little bit of SiO2 without any mask. Then what happens is that at the sharper edge is going to be etched much faster than the other part, so that finally you're going to have rounded patterns like this. And then if you deposit some other layers after this tapering, then we are not going to have residue problem, so something like this. Okay? So we call this process as a tapering. So there is a way to solve the residue problems. Okay. Now, finally, let's discuss about the sputtering and ion milling. Okay. Now, this is a physical process, and no chemical process is involved. This is we have to have a lowest vacuum to increase the mean free path of the sputter element. Like we usually use the heavy ions, but the inert gas like argon, and then we apply the RF plasma, RF to create the plasma, and then this argon ions is going to hit the substrate driven by the self-bias formed by the RF plasma, okay? And then this argon is going to hit the target surface, which is shown here as the cathode, okay? And then the surface atoms of the target is going to be sputtered off by the physical collision between the argon ions and the target atoms. Then sputter off atoms is going to be deposited on the substrate here. And you can immediately see that the deposition rate is not that great in this case. Deposition rate cannot be large in this case, but it does not have any selectivity. It doesn't care what the target atom is. It just due to the physical collision, then the surface atom is going to be taken off from the surface. So that is a sputtering machine. And this is another way to look. The ion beam milling is basically the same thing. The milling is the same thing. It's a sputter off stuff. And in this case, we can have this trenching problem. We call this trenching. This is the materials, and then this is the surface. And then when you etch, here you are going to create the trenches like this. It's supposed to be this flat, but at the edges, you're going to have a deeper etching portion, which is going to be called trenches. And this is important problem with the physical collision etching, like sputtering and ion milling, illustrating the formation of ditches, we call it ditches, in physical ion etching. Okay. And the redeposition, the etched material is going to be deposited somewhere else, where the material has to be etched. So we call that the redepositions. Okay, that's just an intuitive thing that we can expect. This is the schematic illustration of ion milling system, and you can see there is a neutralization of filament. This neutralization filament, it just gives the electrons, supply the electrons to the ions which has been accelerated with the self-bias. Okay, and then before these ions hit the target to sputter off, that ion has to be neutralized with the combination of electrons. Because if you don't do this, then your substrate maybe have a radiation damage, because the ionized atoms is going to hit your surface, the target substrate, then you are going to have a radiation damage. So in order to reduce the radiation damage, what you have to do is you have to neutralize the ions before it hits the target. Okay, that is the ion milling system, and you can see the chamber has to be kept in a high vacuum. It's not an order of torr, 0.1 torr or something like that. It's the entire chamber has to be kept less than 10 to minus 3, something like that. Okay, we summarize the etching process. We start out with the distinction between the wet etching and dry etching here. And the wet etching, it has an isotropic etching, so that dimensional control is impossible with this wet etching. So that's why dry etching has been developed. And in the dry etching, we use a barrel type. Okay, that is a plasma, just a chemical process. Neutral atoms is involved, and typically we have a barrel type and the planar type for this plasma etching. And the barrel type 10 torr, planar type 1 torr. And in the dry etching, we are going to create some of the physical collisions, and that's RIE, ion milling, and those two things is a typical example for the involvement of the physical etching. And the RIE, it has some chemical reactions inside it, but physical process is enough physical process should be involved to have a dimensional control to create the anisotropic etching. And that is the most popular method for the dry etching in the industries. And this is another way to look at this different dry etching technique. We have a chemical process, and at the other end, we have a physical process. And this chemical process, we have a plasma etching, and the physical process, we have a spiral etching. and in between we have RIE and milling. And selectivity, if you go to the physical process, the selectivity is pretty bad because no chemical reaction is involved. And the energies, you need the high energies for the physical process so that the vacuum has to be kept high for the physical process. And that's why this physical processes, equipment for the physical process is usually very expensive because we have to keep the high vacuum. And the energies, we need the high energies for the physical process, of course, because it has to accelerate the ions, okay? So the energy should be high, pressure should be low in the physical process. So that's why this physical processes are usually very expensive, but the very good dimensional control. Okay, this has been summarized that. And here is some of the important thing has been tabulated here, the plasma and the things that we have discussed so far. So you look into this table carefully, and then you can see we have a various dry etching technique, and we can have, depending on the purpose of the etching, we can have choices, okay? And this is the final arrangement for the different dry etching technique. And you can see the important thing here is the selectivity and the edge profile. That is related to the dimensional control, okay? And as you move from here to here, everything becomes expensive because of the high energy and the low pressure. Okay, that is the end of dry etching technique. And we are going to work on the lithography on the page 303. Okay. Then questions? All right. Okay, for dry lithography. Lithography, let me prepare the lithography. Actually, in the introduction, it says, the origin of today high-resolution lithography dated back to 1700. So pre-old technologies. Okay, and lithography essentially is very important in the modern VLSI process because the size of the transistor, we have to create almost the micron-sized transistors for the VLSI. So without this lithography, we cannot do any integrations these days. And on the next page is it has a summary of the VLSI, LSI, designer, CAD, and mask creation, and then this the list of lithographic technique. Contact and proximity aligner. The aligner means it's just aligning the patterns, because in the VLSI process you have to deposit many layers after layer after layer. You have to deposit many layers, and then you have to etch to create the patterns. on the layer. So there is an alignment mark for each mask. For usually VLSI process, you need to have VLSI process. The simplest one is the DRAM fabrication, and for DRAM fabrication you need 7 to 8 mask steps. Okay, 7 to 8 mask steps. So you have to have a repetition of deposition of the layers and then etching of the layers, and each pattern has to be aligned by itself to form a one set of transistors like this. Okay, gate oxide and gate. For example, things like this. Okay, and then the field oxide. You have a lot of masking steps, and this mask, each mask has to be aligned by itself, and then we call that aligner or exposure system. And here's a list of the types of the exposure system. Actually, the aligner, contact aligner, proximity aligner, and the projection printing is another method. And optical direct step, well, the X-rays is another light source we can use, but it's not common in practice. Optical direct step and E-beam direct writing. E-beam direct writing does not need any masking steps, which consists of many steps here, okay? And it just comes from the CAD graphics, and that directly you use the E-beam to create the patterns. And we're going to discuss about this aligner systems in detail in a minute. Excuse me. But here, what is the lithography? Wafer patterning system. How do we create the patterns on the wafer? Okay, you have a substrate and you have a thin film where you are going to imprint or realize the patterns on your mask, and then you spin or the coat the photoresist. The photoresist, here the resist is the photoresist. We have negative photoresist and positive photoresist. We have two kinds of resist. And we're going to talk about the resist in a minute, but anyway, we have a photoresist to cover up the thin film, and then we use the mask. We call the mask. And the mask is going to be prepared on the glass. And then we usually use a chrome metals, okay? And then with the laser, you create a pattern. Sorry, excuse me. The pattern means you just make the part of the chromium layer where the light can pass or light cannot pass. Okay, so you use the laser just to melt down the chromium, and the resolution here is less than 1 micron, of course, because the laser beam can be focused less than 50 angstrom or something. Okay. So you can create a very sharp lines with a high resolution. And then with this glass, we call this mask, okay? And then you use that mask, and then you put your substrate the photoresist here, and on top you shine the light, and then this mask will make the part of the photoresist where the light is going to be passed, or the part of the photoresist is not going to be exposed to the light. Okay, so you can have a photoresist with the light and without the light. Okay, if you use a negative photoresist, then if the light has been shined on it, then the photoresist is going to be polymerized so that it is not going to be developed, it's not going to be dissolved and the chemical afterwards. And if you use the positive photoresist, that means that when you shine the light, the positive photoresist, that part is going to be dissolved and in the developer. Okay, so positive and negative is just the other way around, and we have a choice for that. And then with that, after you expose the lights and develop the photoresist, then use this photoresist. We call that photoresist PR. Okay, photoresist PR. With this PR, we use them as a mask and etching. Okay, then the thin films, which has been covered by the photoresist like this, then only the part where exposed to the etch and the gas in a dry etching or wet etching system, whatever, that is going to be etched so that the pattern of the mask is going to be realized on the thin film, which has been deposited on the silicon. Okay? So if you use the negative photoresist, then you are going to have just a reverse pattern of the mask. But if you use the positive photoresist, then you're going to have the exactly same pattern that you have on the mask. So naturally, what we are going to talk here is we're starting out the negative photoresist. And this is a chemistry stuff, but we are not going to discuss in detail about the chemistry, but we just make an introduction of the photoresist, the nature of the photoresist. Okay, the negative photoresist, it consists of high molecular weight polymer, light-sensitive additive, which promotes a cross-linking, and volatile solvent to aid spin application. Well, that's just to make it liquid with a certain viscosity. Because the way we put the PR photoresist on the substrate is by spin. Okay, you have a rotating thing, spinner, and then you place your wafer to be coated with the photoresist, and then with a little bit of photoresist, it's going to be dropped at the center of the spinning table. Okay, and then with the RPM, how fast it rotates, we can control the thickness of PR. Okay, so we call this a spin coating. That's how you form a thin layer of photoresist on your substrate. Long time ago, people try to use a brush, but with the brush, you cannot have a uniform thickness of the photoresist. Okay? Before that, people try to use a spray. So these days we just use a spin coating or spin coating. And for the spin coating, you need some viscosity of the photoresist, and then to make it show certain viscosity, you just dilute, okay, your photoresist with some crystalline and things like that to control the viscosity. I'm losing my voice. Well, so this is a high molecular weight polymer with some promoters. It has been written as a P here. And then by shining light, this promoter will cross-link of these high molecular chains so that it really become a heavy molecules. So with a developer, it is not going to be dissolved. The portions of negative photoresist with the light, it will have a cross-linking promoted by the promoters and become very heavy materials. And so the part of the negative photoresist with the light will not going to be dissolved in the developer. Okay? That's how you can create the patterns with exposure. The typical negative working photoresist is a mixture of polymer molecules represented by the wavy lines on the top figure, and the molecules of light sensitive, polyfunctional additive there, and this is dissociation reactions, and then you have this radical, and with the light energies, then it becomes this radicals, which is going to promote the cross-linking. Okay? So the light-sensitive additive P is typically this radicals. Okay? And then we don't have to understand the details of this, but it just, you can see the amount of additive and the sensitivity of this polymerization with the light wavelength. It should have some sensitivity, so something like this, okay? And you can have the polymerization rate with some simple equation, and then this equation I don't think is important. Anyway, so that is the experimentally observed thing, single bonds and cross links, that is depending on the energy of the lights. You can have experimental later data like that. And then just the etch rate in the developer is depending on the cross links that has been created with the light. Now, you just carefully look at this, okay? The advantage of negative photoresist is very sensitive to the light, means you don't have to shine the light for a long time. And this timing, exposure times, is very important, very much closely related to the throughput, because you are going to have typically about 100 dyes to be exposed with the light for each masking steps. okay? And for each die, if you spend a certain amount of time, then it should be multiplied by 100 to finish one wafer, okay? And then that has to be multiplied by the masking steps that it has, like 7 to 8 masking steps, for example. Then it has to be multiplied by the 7 to 8, which means you end up with 700 or 800 times of each exposure time. Okay, so this is very much related to the throughput in the industry. So it's not a trivial question at all. Relatively tolerant of developing conditions, because developing is the area without polymerization is going to be dissolved in the developer. And so originally the negative photoresist is made easy to be dissolved in the developer. So we have relative margins, in the developing the area of negative photoresist without light exposure. High etch resistance. The polymerized part is not going to be etched at all because it has a heavy, it becomes a heavy molecules. Now, the disadvantage is important. Adhesion to the substrate depends on the cross-linking reaction, may need to overexposure to penetrate through films. Okay? This means now, if you have a substrate and you have a thin film to be etched, to be patterned, and then you're going to have a PR, okay? Well, for the dimensions that we are talking about, we must say the thin films that should be is about 1,000 angstrom unit, okay? 1 or 2,000 angstrom, something like that. The PR is more than 1 microns, usually. So the thickness, you can have a relative figure how thick we're talking about here, the PR and the thin film. Now, with the mask, let's suppose you have some part is exposure to the light, and this part is exposure to the light, and the other part is not exposed to the light. Then if you use a negative photoresist, it means that you're going to have a cross-linking of all this part with the promoters. Okay, it becomes heavy molecules. And this part is going to be the original photoresist because it has not, polymerization has not happened in this area. And if you put it in the developer, we call that the developer, okay? Then this part is going to be dissolved in the water here, developer, and then the exposed part is not going to be dissolved in the developer. And then you put this whole thing, into the etchant to etch the thin film so that you are going to have this materials of thin film, this part, and the other part is going to be etched by the etchant. Okay, that's the way how we create a patterns. Okay. Now the problem with the negative photoresist is that this part where the reaction, polymerization, that is a kind of a reaction product, okay? This reaction product is important. So if anything happens in this reactions, polymerization, then they're going to ruin the resolution of the pattern. And typically two things can happen. The one thing is when you shine the light, depending on the thickness of this or depending on the light intensity or the width, depending on the width, the light may not be enough to penetrate all the way through here. So that this polymerization can happen to the top surface, but not entire thickness, so that a certain layer at the very close to the thin film may not be polymerized. And that is depending on the width. If it is too narrow, then the light is not going to penetrate enough. And if the PR thickness is thick, same thing happens, and things like that, okay? And the light intensity, if the light intensity is not enough, in other words, the exposure time, if you set the too short exposure time, then this thing will happen, okay? If this thing happens, then the adhesion of this negative photoresist to the substrate is not good enough, so that during the developing, this pattern, the photoresist is going to fall off from the surface. So there is a good possibility for the negative photoresist, and that is the main disadvantage of the negative photoresist. Okay, and the second thing is, with this polymerization, the volume is going to be changed. Volume change is inevitable. It goes where the volume change. So we call that the swelling of PR. So it becomes something like this, okay? Then it's going to ruin the resolution as well. And those two things are typical disadvantage of the negative photoresist, even though the negative photoresist has many advantages, like good throughput and things like that, okay? So, in modern VLSI, for the high resolution devices, the negative photoresist is not going to be used, because we cannot take a risk of, we cannot sacrifice the resolution. In the modern devices, the resolution is the most important thing, okay? So, before this, we just talked about the dry etching technique. And the dry etching, the industry people tend to move to the expensive machines like sputtering and ion milling and all those stuff of the physical dry etchers, just because the resolution becomes tough and tough as you move to the modern devices. So sacrificing the selectivity, people tend to use the high resolution dry etchers and sputtering or the ion milling, things like that. The same token, the negative photoresist is cheap and has a good throughput, but people try to use the positive photoresist just because people do not want to sacrifice the resolutions because of this disadvantages. Okay, on Wednesday, we're going to talk about the positive photoresist. We're just going to pick up from here. Okay.